Okay. Can you see it? Okay. So, so we're discussing Toeplitz kernels, and this is Hayashi's theorem. So Hayashi's theorem says that any Toeplitz kernel can be represented as an image of a model space by a symmetric multiplier. So, by the way, just a sort of informal comment. Well, I'm a relative newcomer to this area, but my impression, nevertheless, is the following: that model spaces, they're extremely nice. They have this rich structure and so on. But nevertheless, they are it's probably a rather still relatively poor selection of spaces to construct reasonably rich theory. So, but these spaces of this form, images by asymmetric multipliers of model spaces, this is sufficiently rich. You could think of them as building blocks for any reasonable theory in Hardy space. So that's kind of my intuition into this. So they still have some structure, but they're much more versatile than just model spaces. And so it happens that, at least for Hankel and Toeplitz operators, they do the job in terms of description of the spectral, the subspaces. Okay, so now let me give the proof of this, of Hayashi's theorem. And this is the proof relies heavily on Heath's theorem. So, okay, so proof. Proof of Hayashi's theorem. And so the first point is to check. Let's check that the kernel of the Toeplitz operator is nearly star invariant, nearly a star invariant. So let me just write it explicitly what it is. So this was, remember, our definition of nearly a star invariance. Okay, so this is very easy, in fact. So we suppose, okay, we move it somewhere here. So we suppose some element f is in the kernel. So suppose we have Tf is 0, and also f is orthogonal to 1. That is, f vanishes at 0. Then, importantly, so from the second property, we get that f is S star f. So just to remind you, so S is forward shift, S star backward shift. So if you apply first forward shift and then backward shift, you come to the same element. But if first you shift backwards and then forwards, you kill the constant elements. Okay, but if you're constant Fourier coefficient, the zeroth Fourier coefficient, but if your zeroth Fourier coefficient is already 0, that's precisely what orthogonality to 1 means, then if you move backwards and then move forward again, you come to the same element. Okay, so using this simple fact, we just apply the this identity, the defining identity for Toeplitz operators, to S star f. Okay, so let's do this. So I write S star T S applying to S star f equals T S star f. Okay, now as I said, because S star f is f, I can rewrite this as S star T f equals T S star f. And because Tf is 0 by assumption, because f is in the kernel, so that means T S star f is 0. We are done, right? Because we've checked that S star f is in the kernel, right? So what did we have to check? That we start with f, which is in the kernel, orthogonal to 1, apply S star, and we are still in the kernel. That's precisely what we checked. Okay. So the kernel is nearly a star invariant subspace. So by Heath's theorem, there are two possibilities. Either we have that the kernel of T is p k theta, or it is p h2, that is the whole space, where p is some inner function. Okay, so let's check that the second possibility is not possible, is actually false. Let's eliminate it. Okay, so I don't know if I can squeeze it into this line, so let me see if I can squeeze it into this tiny space on this slide. So suppose we have suppose we have F in H2, and suppose we have that this is 0, where P is an inner function. So this means that P applied to A P F equals 0. So that means that A P F is orthogonal to H2, so it is in this space, right? This is the orthogonal complement to H2 in L2. And then since P is inner, we can rewrite this as AF being in P bar, Z bar, H2 bar. So now if we, now the right-hand side is anti-analytic, right? So if we apply P, the projection, again to this, then we get that TAF is 0, right? Because the projection kills the right-hand side. And so we've started from an arbitrary element in Hardy class, and we've checked that our Toeplitz operator kills this arbitrary element. So that means our Toeplitz operator is simply 0. Okay. So that means that this second possibility is actually not realized. Well, it's realized only in the trivial case when the Toeplitz operator is 0. So we are done. We've proven Hayashi's theorem. Okay. Any questions? So if not, then I will move to Hankel operators. Okay, so I'm moving to Hankel operators, but first I need to discuss some preliminaries before we prove an analogous statement to Hayashi's theorem. I need to do some preparation. So first of all, it will be convenient to deal with an antilinear representation. Antilinear representation for Hankel operators. So this is not something terribly deep. If you want, it's just a question of language or a question of notation. But nevertheless, it's very convenient. For example, remember that we had this when we discussed model spaces, there was a natural antilinear involution on model spaces. And so it's convenient to have the structure of the definition of Hankel operators aligned with this antilinear involution. So we will make them antilinear. Okay, so what does it mean? So remember that originally we defined Hankel operators like this. P A times FZ bar. So now I want to consider another version. This one, okay? So these are, as I said, these are Hankel operators, right? G for Hankel, and this will be Hankel operators. Okay, let's make this distinction. So the Hankel operators are linear, and the Hankel operators are antilinear, because if you multiply f by a constant, this constant gets complex conjugated. Okay, so what is the difference between these guys? So normally, when I first started doing this, I was working with Patrick Girard, and he was using this antilinear representation. And I was just going crazy with this because it's not clear what are eigenspaces, what is spectral theory. Everything seemed anti-intuitive. But gradually I got used to it. It's not such a big deal. It's just a matter of language. So let me just explain what is the difference between these two points of views on Hankel operators. So if you have a function in the Hardy class, so you have this, then what is the difference between f of z bar and f of z bar, right? So f of z bar is the sum this, right? So you put complex conjugation of the coefficients, but also over z, and that z gives us a minus. And if you write f of z bar, you get just a minus. So the difference between these two formula is just that you take a complex conjugation of the coefficients. Okay, so in other words, if you define an antilinear operator C, script C on a Hardy class, which just maps which just acts as a, sorry, Z, n should be on top, yeah, n should be here. So this which just maps, which just gives you complex conjugation on coefficients. So then, with respect to this, I can write that my Hankel operator is a Hankel operator. So it's an antilinear involution followed by the Hankel operator. Okay, that's the thing. So that's the only difference. Now it is easy to see. Now I will try to explain why it is convenient to use this antilinear representation. But first of all, notice that the matrix of Hankel operator, of Hankel operator, right? I should say this matrix. Remember, it is A0. Then A1, A2, and so on. So this matrix is symmetric, right? It's not Hermitian, of course, but it's symmetric with respect to transposition. So taking the adjoint of this matrix is the same as just putting bar over all coefficients of this matrix. It's taking complex conjugation of this. So using this, it is straightforward to see that we have this relation, okay? And so it's important from here that the square of this antilinear operator, I can write it like this. So this is the square. Now using the line above, this is just gamma A star, okay? So of course, this operator, this Hankel operator is antilinear, but when you take square, it becomes linear, right? When you do complex conjugation twice, you get back to the same thing. And in fact, not only it's linear, but it's also, of course, self-adjoint and non-negative, okay? And so as a consequence, if we are talking about Schmidt subspaces for for gamma, or more precisely for gamma star, then this is the same as talking about the kernel of h squared. And so as a consequence, HA squared acts on this subspace, right? It acts from this kernel to itself. And this is the advantage over the linear picture, because, sorry, this is not HA squared, this is HA, right? So it acts on this subspace, on this kernel itself. This is the advantage over the linear picture, because in the linear picture, remember that here we had that gamma A acts from one subspace to another one. And so it's convenient to fix the subspace and work, and then we pay for this by having antilinear operator. So this is really just a matter of notation, or a matter of language, if you want, nothing else. The second point about notation is that it will be convenient to assume that A is analytic, because then this fixes the symbol uniquely. And in this case, we see that this A is gamma A of applied to identity, because this P, A, or HA, in fact, right? We've switched to HA already. So let me switch to HA. HA applied to identity, because then it's very easy. It's just PA, which is A. Okay, and finally, in what follows, I will switch the letter and I will use U, because we use U in our paper everywhere, and I have U in my notes, and if I try to switch to stick to A, I think I will get confused. So U will be the analytic symbol of a Hankel operator. So we will be dealing with HU. HUF, once again, is P of U F bar. Okay, so this is kind of notation out of the way. Next point. Let's just start our discussion by discussing Hankel kernels and ranges. So once again, HUF is P of UF bar, and we have the key commutation relation. Okay, so I wrote it for a linear version, but in the antilinear version, it remains exactly the same. So let's first discuss kernels, like we did for the Toeplitz operator. So kernel, what is the kernel of HU? How to identify it? So if we have an element in the kernel, so if HUF equals 0, let's apply the commutation relation to it. So we have S star HUF equals HUSF. The left-hand side is 0 by assumption, and so the right-hand side is also 0. So that means that SF is also in the kernel. So we see that S maps the kernel of HU to itself. And that's it. That's Berling's theorem. Okay, so by Berling's theorem, such a kernel can always be written as some in the function. Let me give a different name. So psi instead of theta, psi inner. Okay. So now, because the range of an operator is the orthogonal complement to the kernel, rather the closed range, we see that the range is the model space. So in some sense, when you look at the action of a Hankel operator, everything takes place in a model space. Okay. Let's consider one example, like we did in the Toeplitz case. Let's consider Hankel operator whose symbol is an inner function. So these are the simplest possible Hankel operators, as you will see in a minute. In the following sense that, so what is the action of theta? So of this Hankel operator, this is this P theta F bar. So it is, in this case, it is straightforward to see that the kernel is precisely this. So this is almost what we had in the definition of this antilinear involution up to z. Okay, so z, we have this z. So the kernel of h theta is this subspace, and the range is precisely the model space K z theta. And h theta acts precisely as an antilinear involution on this kz theta. So h theta f is theta f bar on, so when f is in this subspace. So in this simple case, right, our Hankel operator is just an antilinear involution on this model space. So in particular, its square is just the projection onto this model space z kz theta. So in particular, the spectral structure of this Hankel operator is very simple. You have only one singular value, which is 1, and the corresponding Schmidt subspace, singular value 1, and the corresponding Schmidt subspace corresponding to 1 is just this model space. Okay. So as we will see, these are kind of such Hankel operators with inner symbols. They are sort of building blocks for spectral theory of more general Hankel operators. Okay, so now let me finally come to the main result. Schmidt subspaces of Hankel operators. Okay, Schmidt subspaces of Hankel operators. So this is the main theorem due to Patrick Gerard and myself. A couple of years ago. So let HU, so HU be a bounded Hankel operator. And we have that S is a singular value of HU. Singular value of HU. That means the corresponding subspace, the kernel of HU squared minus S squared identity is non-trivial. Then the subspace can be represented as P k theta, where theta is inner, and P is an isometric multiplier on k theta. So they have the same form as Toeplitz eigenspaces. Same form as Toeplitz eigenspaces. There are some important differences. When you look at the structure of these P's, you see that there are some differences, but nevertheless, overall, they are from the same class of subspaces. Okay, so I will prove it relatively easily based on Heat's theorem. But first, let me make a little remark before the proof. So these Schmidt subspaces may or may not be nearly S star invariant. And if they're not S star invariant, this happens because it may happen that they're actually orthogonal to 1. There is an example in the lecture notes where it's a very simple, just a rational, very simple rational function where you have exactly this situation. You can actually compute it and see that the corresponding Schmidt subspace is orthogonal to 1. So I will give a proof in the case when this Schmidt subspace is actually not orthogonal to 1, and then I will comment on what to do if there is this orthogonality. Okay. So yeah, so let me first prepare some identities. So first, let me remind you. So this is what I used in some sense for in our proof of Hayashi's theorem. So remember that we have. So this is easy. This is just to say that the backwards shift is an isometry, but if you write them in the opposite order, you get the difference by rank 1 operator, which is just multiplication by identity, right? So if you shift backwards and then you shift forwards, you end up with the same vector, but you have to subtract the constant term. Okay, so next, let me just remind you that HU acting on the identity gives U. And we also have the commutation relation for Hankel operator. So using this, I want to establish some identity that I will need in the proof. So let me compute the following thing. Okay, I want to compute this product. So what I will do, I will move S star and S inside. So let me write it like this: is S star HU, HU S. And in both of these terms, I will use this commutation identity for commuting S star and S inside, right? So then HU will be outside and S star will be inside, but S star will become S and S will become S star. So I get SU, S, S star, HU. And now remember that we have this identity for the product that I've got inside HU. So I continue. This will be HU, identity minus dot 1, 1, HU. And so this becomes HU squared minus dot HU1, HU1, and HU1 is U. So this becomes HU squared minus dot U. Okay, so this is a simple rank 1 identity. So here I want to pause and make one important remark, that in this theory, it is very important that the symbol of the Hankel operator appears not just as some sort of separate element from L infinity or H infinity, but it appears as an element of the Hardy class, as an element of our Hilbert space on which HU acts. Okay, so when you work with Toeplitz operators, for example, you mostly think as a symbol being separate from the Hardy class, right? It's just something that you multiply. It's a multiplier. So here it's important that U actually appears as an element of the Hardy class. Okay, so now using this identity, I want to do something else. Oh yeah, and by the way, very important thing, very important insight. So compare this with the identity for Toeplitz operators. Okay, so you see that the square of this Hankel behaves a bit like Toeplitz up to rank 1. So the heuristics here is that really spectral theory of squares of Hankel operators is a bit like rank 1 perturbed spectral theory of Toeplitz operators. Okay, so this is why the results, for example, eigenspaces of Toeplitz operators should be compared to Schmidt subspaces, not eigenspaces of Hankel operators. Okay, so the result, as we will see, is the same in terms of the structure, is the same, but the proof is a little bit more complicated because of this rank 1 business, this rank 1 perturbation. Okay, so I need to develop this identity a little bit more. So let me move to the next page. So I will repeat what I've just had here on the previous page. So I had S star HU S HU squared S equals HU squared minus dot U. So I will do one more thing. I will multiply this by S star on the right. So I get S star HU S star equals HU squared S star minus dot SU U. And then finally, remember that this is 1 minus projection onto 1. So I've got S star HU. Now I move this term to the left-hand side, minus HU squared star, and I collect all the rank 1 terms on the right-hand side. So what I get is dot 1 S star HU U minus dot SU U. So the exact nature of this, sorry, this should be, I missed square somewhere, square here and square here, yes. So the exact nature of what's on the right-hand side shouldn't worry you too much, but the important point is this, that we see that S star, the backward shift, commutes with HU squared up to rank 2, okay? So in the Toeplitz case, it was rank 1, here it is rank 2. So the algebra is a little bit more complicated. So, so this is, we've done the preparations for the proof. So now we proceed with the proof. Proof of the theorem. So we want to prove. So we assume that our Schmidt subspace is not orthogonal to 1. And let's prove that it is nearly a star invariant. So when we are done, I will explain what to do when you actually have when this condition doesn't hold. So as a first preliminary, okay, let's do this. Let me go right away with the key calculation. So I want to take this identity. Let me put it in the frame so we can look at it. So this identity in the blue box, and I will apply it to two elements f and g from our from our Schmidt subspace. So f and g are in the Schmidt subspace. So the reason I'm doing these calculations, I want to give you a taste of how this theory works. It's very, very algebraic. So let's apply this to f to elements f and g to look at the quadratic form of this tested on the elements f and g. Okay, so just write down the left-hand side. And then I've got the right-hand side. Okay, now let's look at the left-hand side first. In the left-hand side, so hu squared f is just s squared f, because remember we are in the Schmidt subspace. So hu squared f equals s squared f, hu squared g equals s squared g. And so because of this, for the left-hand side is, we get s squared s star f g. And then in the second term, I can move hu squared to the right. Remember, it's a self-adjoint operator. And then I use the same identity here. And so what I get 0, right? Because this is also s squared s star f g. So I get 0. So my left-hand side is 0. So that means that my right-hand side is 0. Okay, so now imagine that f is orthogonal to 1, right? So let f be orthogonal to 1. So I am sort of getting to the proof of this inclusion of the nearly star invariance. So let f be orthogonal to 1. Then this term disappears. So this term disappears. And I've got just, it means that this remaining term is 0. So it means that f su times ug must be 0 for all g. So now I want to kill the first the first inner product here. So for this, I need to ensure that I can choose g such that this guy is non-zero. Let's find g in our subspace such that UG is non-zero. This will follow from our assumption that we are not orthogonal to 1. Okay, so suppose we've chosen an element which is not orthogonal to 1. So let H be in the Schmidt subspace. H 1 is not 0. Let's take for G HU times H. Remember that HU acts on our Schmidt subspace. And so this G will be still in the Schmidt subspace. So now let's compute the inner product, G and U. So this is HUH and HUH U. So yeah, so let me do this as follows. Sorry. So let me write it as GU. So GU, this is the following thing. This is G, this is 1 times U G bar. Now I'm thinking of this inner product as a product in L2. And I've just moved G to the other part and put a bar over it. Right? So now because 1 is analytic, I can write it as 1 P U G bar. And now on the right hand side, I've got the Hardy, the Hankel operator. This is my HUG. Okay. And G was HUH. So this is 1 HU squared H. Okay. And because because we are in the Schmidt subspace, HU squared H is S squared H. So I've got this. And by assumption, this is non-zero by this assumption. So I found an element G such that the inner product G dot U is non-zero. So this term is non-zero. And so as a consequence, this must vanish. F, comma, SU must vanish. So let's take stock of what we've computed. So we've started with an element F, which is in our Schmidt subspace and which is orthogonal to 1. And so now let's look at the right-hand side of, so now let's act by this operator in the blue box on F. So the left-hand side, it is what it is. On the right-hand side, of course, F is orthogonal to 1 by choice. And we've just proved that F is orthogonal to SU. So the second term also disappears. So what we find is that if we apply to this operator in the blue box to F, then the right-hand side just disappears. Okay, so we find that as a consequence, S star HU squared F equals HU squared S star F. Okay, and this is S squared F. So what we find is that S star F satisfies the eigenvalue equation for HU squared, right? We've got that HU squared star F equals S squared S star F. And so S star F is, as required, is in the Schmidt subspace. right? Because satisfying the eigenvalue equation is precisely means that this is our definition of this Schmidt subspace. And so we've checked that our Schmidt subspace is nearly invariant. Okay. So now again, by Heath's theorem, there are two possibilities. So by Heath's, either this Schmidt subspace is pk theta for some where p is an isometric multiplier on k theta, or the second possibility is that it may be some inner function times the whole of h2, but then it's easy to check. So in my notes, it's stated as an exercise with some hints that the second possibility is actually not realized for Hankel operators. And so we come to the end of the proof. Okay. So this completes the proof. So we've described the structure of Schmidt subspaces of Hankel operators. So the only thing to note is, as I said, we've done it in case there is no such orthogonality. So we have to look at the case when there is this orthogonality. So imagine that this subspace is orthogonal to 1. So what does it mean? So suppose is orthogonal to 1. So note that 1 is a reproducing kernel at the point 0. So you just have to find another reproducing kernel to which this subspace is not orthogonal. Clearly, you will be able to find such a point, right? So that you will be able to find another point such that not all functions in your subspace vanish here. So we have to find alpha in the unit disk such that this subspace is not orthogonal to the reproducing kernel at alpha. And then you make a Möbius transformation sending alpha to 0. And then you repeat the arguments of the first part of the proof. So then you will see that after this Möbius transformation, your Hankel operator will transform to another Hankel operator whose Schmidt subspace will not be orthogonal to 1, and then you repeat the same arguments. So that's the idea. So again, in the notes, I wrote out some details, but here I will not do this. Okay, so I have 10 minutes left. I'm just wondering what to cover in these 10 minutes. So I think I want to speak about inverse problems for Hankel operators, which was the motivation for all of this work. Okay, so this will be. So normally motivation comes at the beginning, but here we'll put it at the end. Motivation inverse spectral problems for Hankel operators. So this whole activity about characterization of Schmidt subspaces of Hankel operators came as a so originated from the work of Patrick Gérard and Sandrine Grillier. So let me say a few words about this to motivate. So Patrick Gérard and Sandrine Grillier had a sort of a series of papers in this period. So first they introduced an equation which they called the cubic Segue equation. Cubic Segue equation. So this was the equation. So u is a function of z and of time. So z is a variable on the unit circle, and time, so t is time. So this is a nonlinear evolution equation, and they used it as a sort of a certain model for totally non-dispersive evolution equations. So here u for each t, this is an element of the Hardy class, and P is our usual projection onto the Hardy class. So you take, first you take U, you square it, and then you project back onto the Hardy class. Of course, it has to satisfy certain regularity conditions so that this operation makes sense. So the fundamental discovery was that this equation is actually completely integrable. So this turned out to be completely integrable. And so they discovered the Lux pair for this. So this is the equation equivalent to the cubic Segue equation. So here HU is our friend, a Hankel operator with the symbol U, and BU is some certain auxiliary skew self-adjoint operator. It's something that's made up of turplets and Hankels. So the important point is that all spectral properties of HU, not all spectral properties, okay, singular values of HU are integrals of motion for this equation. Okay, so let's assume that we're working on the class of U where U is compact. So if U is such that HU is compact, we assume this, and then the singular values of HU are conserved by these dynamics, the integrals of motion. So now you want to apply the usual method of inverse problem to solving this Segue equation. So you need to be able to solve very well the direct and inverse spectral problems for this Hankel operator HU. So you need to develop direct and inverse spectral theory for this HU. And this is what Patrick and Sandrine have accomplished for compact Hankel operators. Then I joined this team, and we kind of made it a little bit more precise, and not necessarily we've extended to a larger class, to some non-compact operators. But this is a history, but what what I want to say is that how is this? What are the exact? What are these inverse spectral problems, and how are they related to what I was talking about? So suppose you have a compact Hankel operator HU. So then, as we know, its range, its closed range, will be some model space, and so we can write this model space as an orthogonal sum of maybe finite, maybe infinite Schmidt subspaces corresponding to the what did I didn't put square, so corresponding to the singular values. Okay, so each of them is the kernel of this. And so by the theorem that we proved in these lectures, each of them can be represented as Pn k theta n. So remember that Pn and theta n are not unique, but if we normalize like this, then these parameters become unique up to unimodular constant factors. So we have this decomposition. Okay, so it turns out that you can parameterize your Hankel operators by looking at these functions appearing here. Okay, so more precisely, let me, what you need to use is the sequence of singular values and the sequence of those inner functions. This is the spectral data. Turns out this is not a complete spectral data. You need to use something else. So here is a very nice analogy. Note that in, for example, in Borg's theorem for inverse problems for a Sturm-Liouville operator on the interval 0, 1, how do you recover the potential? You need to know two sequence of eigenvalues for two sets of boundary data, right? So if you have Dirichlet and Neumann, then you can Dirichlet eigenvalues and Neumann eigenvalues, then you can recover the potential. So here the situation is similar. You need to know these data for your Hankel operator and for another one, for an associated operator, for this guy. Okay. So you apply backward shift to your symbol. Then associated to this guy, this guy will also have some singular values and some inner functions appearing in the spectral analysis of this operator, of the HS star U. And so it turns out that altogether, this is a complete and independent set of spectral data. Okay, so this determines uniquely your symbol. So conversely, pick any sequence Sn, any sequence of Sn tilde, they have to interlace, right? This is a very simple condition. They have to interlace, and pick any sequence of inner functions, theta n and theta n tilde. So the only condition is that they have to vanish at 0. They don't even have to be finite rank. Then from this, you can construct uniquely a symbol U for which these guys, these inner functions and singular values describe the spectral decomposition of these operators. So these isometric multipliers Pn, somehow they don't appear here, right? They don't feature in this inverse problem. So you can, in principle, express them in terms of these spectral data with their explicit formulae. Not so simple, but there are some. So this is why we, this is the for us to start looking into this. And this decomposition, this representation of Schmidt subspaces as images of model spaces by multipliers, this was absolutely central to this, because without this we cannot prove. There's a lot of algebra in all there on this isometricity of the action of P. Okay, I think I said all I wanted to say, and this is time for me to stop. Thank you very much.
Спасибо. Thank you.
Спасибо. Спасибо.
Спасибо.